I will just let you know the publisher name. Title of the book is HDL Programming, VHDL and Verilog. You need not study VHDL from this textbook for syllabus point of view. If you can study simply Verilog, it is fine. Wherever there is a Verilog sections, you just highlight or tick mark that topic and study only Verilog related. Look at the syllabus. Only Verilog has been covered in your syllabus. No need to study the VHDL. VHDL is another hardware description language similar to Verilog, but that was one of the widely used language during our days, our times. Okay. In fact, I learned the VHDL first, and Verilog the research has demanded for me to learn Verilog. Maybe I have spent almost 8 to 10 years learning Verilog. But in fact, if you know VHDL, learning Verilog will not take much time, because the syntax, semantics, everything, the Verilog, it's very easy to learn. In fact, VHDL is difficult to learn, okay, because the syntax and semantics, it's old style. Okay. Though the VHDL is used in academia, but Verilog is popular in industry. Okay. Those who want to join the digital design industry, to do like digital design things, you want to learn this Verilog, because Verilog is one of the most widely used hardware description language. Okay, there are various styles to write the Verilog program. I will just teach you for different methods to learn the Verilog. But our syllabus starts with the little bit of history, then we will move on to the actual language. The author is Ms. M. Bathos. He's a very old author. Many times I interacted with him and he has supplied me the PowerPoint presentation, but I somehow missed his PPT he has sent long back. When first time this textbook came, probably in the year 2010-11, I believe it. At that time itself, I approached the author to send me the solution manual and PPTs. From 2007-8 to till date, a lot of changes happened in my system, and I don't know how I missed it. All PPTs shared by the author I missed it, and I think he works for some popular university. I don't remember the university for which he was working, and he's basically a biotech author, and he has attempted his modeled digital design, developed digital design for the biology related things and many stuff like that. If you look at his profile, you will understand better. Normally, earlier, when I first teach the subject, first time I used to go through author background, author, which area he works, what is his research interests, and what are the things he has developed. All those things I used to watch. Basically, he's a biological person, and he has modeled. He used Verilog and VHDL to model those biological things. Okay. But here you are learning from generally the Verilog programming language for doing digital design. Remember, this is not a very difficult language, and this language is learned only by electronic students. Even though I taught this course in computer science long back, not now, but still they didn't show much interest because they are more, they are aligned with software programming languages rather than hardware description language like this. But this is a language which every electronic student should learn. Electronics and allied branches student should learn. The reason is very simple, because you'll be using this digital part, in one or other, maybe there were PBL or project or industrial development kind of things. I suggest you to learn this as and practice this, and slowly if you start with simple designs to begin with, and later you can go for complex designs. Okay. Remember, I started by developing simple adder and simple multiplier, and when I started my research career, my guy told me you should not do only simple things, you should go more to jump to the complex things. Okay. Then I told he gave me one FR filter, very popular filter in DSP's FR filter. He told me to develop and come. Okay, so I written old way of programming, and he blasted me and told this is not the way you are supposed to write the code. And he taught me, he has authored a book, and he shared me the book to me and told follow that book sincerely, and you will become an expert in that. Believe it or not, I followed that book sincerely. I think I can say in 1 to 10 in RTL programming, I stand at 8. But I don't do any coding for industry. but I give sometimes guidance to the industry, how to write, RTL kind of programming style. I'll show you some of couple of designs what I've done. Okay, I started with, as I told you, simple. You also can start with simple adders, multipliers. I'm sure that for multiplier I've done variety of multipliers I've developed, and a couple of multipliers are published as a paper also. Okay. Anyway, that's my part. Let me move on to the syllabus. This book is just teaches you the basic fundamentals, but you cannot go to the research level by just learning Verilog from this book. Just from syllabus point of view, this book is very good. Let me tell you, I learned fundamentals, basics from this book. Okay, you also can focus on this book. Author is very good. He has nicely covered both VHTL and Verilog aspects. Dream Tech is the publisher. This book is not. I searched to find it in online. I mean the PDF copy of this book. I could not find it. I thought let me take a photocopy. I mean the scan it this book and so that it will be useful for you. Okay, that's the thing. I started from. I have not scanned the contents of this book, but only relevant things I have scanned here, and which is as per the syllabus. Let me start with this introductory part. That's our first part of the syllabus. I mean the module 4, what we are covering right now. In module 4, we start directly from the structure of the Verilog, but I want to give you a little bit of history and later move on to the structure of the Verilog program. History will not take much time. I made few couple of points so that you also get familiar with this, Verilog. Okay. Before that, you need to understand two things. What is HDL first? HDL stands for Hardware Description Language. It's clarified here. Hardware Description Language. HDL. Shortly, we can call it HDL. Okay. Why this HDL is used? It's basically today's design is computer-aided design. It's not manual design. What is manual design? You're doing laboratory. By going to the laboratory, you ask instructor to give some ICs, right? 74 series ICs, and you build. You might have already have a logic circuit with you, a logic diagram with you, and as per that, you collect different ICs from the instructor, and you build the circuit and the training kit, right? This is what normally you do. Understand it? But if I give you a small circuit, you can do that. But what if I give you a very complex circuit? If I ask you to build, like as I told you, FI printer or IR printer, generally if I ask you to develop some small GPU or small CPU or ALU for that matter, can you go to laboratory and build ALU? Here, no, I don't think it is possible to the trainer. Even if you want to do small level of operations like 8 operations, 10 operations in ALU, like simple addition, subtraction, multiplication, division, increment, decrement, and moving data, all these kind of things which normally ALU will do, arithmetic and logic unit of the computer will do. If you want to develop similar kind of ALU, you can't go to the digital lab and do this kind of things. Understand it? That's called discrete IC design. If you look at this, you'll understand better. Whatever I'm covering is discrete integrated circuits. Because of complexity, you cannot move to the discrete integrated circuits. Okay. As complexity increases, you have to move to the automated kind of designs. What is automated? You write some program and you allow the tool to do automation. Okay. It will generate circuit for you. It will design circuit for you. Your idea, your objective must be expressed through the programming like language. Understand it? That's a concept here, the meaning of it. You're writing a program using HDL and that will automate the things. And once you have developed, the automate the designs, you have to download that automated designs onto some the boards, right? I mean the ICs you want to develop. There are two things which you need to understand here is application-specific integrated circuits, and another one is going to be the field programmable gate arrays. What do you mean by field program? There are two different ways you can do digital designs. One is ASIC part, which we call as application-specific integrated circuit. What do you mean by application-specific integrated circuit? They are the integrated circuits, ICs, which are meant for specific applications. What do you mean by specific applications again? If you're building, the IC for some toy or for some washing machine or for some oven, okay, so these are called application-specific. You're not generalizing the ICs, understand it? This is, for example, if I'm building IC for the laptop, it is generalizing. Understand it? I don't want to generalize. If I build, IC dedicated to say for this project itself, that's application specific. If I develop an IC just for some satellite applications, it is specific applications. Understand? You understand difference between general application and specific application? Okay. All those nothing what I'm saying is IC is meant for application specific. Understand? It depends, circumstance, it depends. If you go to the industry, they will not tell you to build general ICs. They will give some application and ask you to build IC for that. So those are called application specific ICs. If you ask me, can I call 74 series IC 7486 or 7404 ICs as application specific? You can't call them because they're all general purpose ICs. Understand it? Which everybody will use it. They're not meant for specific applications. You can customize for your application also. You can customize for any applications. So they are not general purpose. They are general purpose ICs. Application ICs are totally different. I hope you understood the meaning of application specific integrated circuits. ICs can be classified into two types. One is application specific. Other one is FPGAs. FPGA stands for field programmable gate arrays. Understand? They are the again ICs which are not programmed, which are unprogrammed. It will be of size, just like this laptop, or sometimes depending on complexity. FPGAs will be small ICs. It will come with small ICs with all necessary interfacing, programming aspects. It will come. Understand? FPGAs comes with a tool also. You should have a relevant tool corresponding to the FPGA. FPGA is normally small board, just like your microprocessor board. Understand here? There are a lot of difference between the microprocessor, microcontroller, and the FPGAs. Many times when you go to the industry, they will ask you this question: what is the difference between microprocessor, microcontroller, and FPGA? And if I give you a design to you, which one you will choose the platform? Will you go for microprocessor, or will you go for microcontroller, or embedded system, what we call, or will you go for FPGA? How do you choose now? Depending on applications. You have to choose, you have to see the application, and depending on application, suppose if I give you a project like simple automatic door opening and closing project, which one you will prefer? Simple microcontroller. You don't want to go for FPGA, right? Understand? If I give you something like an IR filter design or a 50 design, fast Fourier transform design, will you go for microprocessor? Will you go for microcontroller? You go for FPGA normally. Understand it? Now you understand now, when complexity keeps increasing, when small, tiny things are there, you will not go for FPGA. Understand it? Even see, I am showing you here how to design a gate, logic gate, but using that you cannot go for FPGA. Only you can simulate and run and see the results, that's all. But you are unable to, you cannot make that as commercial ICs. AND gate IC, OR gate IC, you cannot use that for FPGA. You can simulate and run and see the results. Understand here? So depending upon your complexity, you can choose different ways. You can the ICs, either application specific or the FPGAs. And right now, I don't want to teach this application specific integrated circuit. In the higher semester, you will learn, especially we have a cadence tool here in our department, which is a very complex tool. I mean, to learn. But once you learn, once you become master in that, there will be a lot of job opportunities in the tool, using tool itself. And you can build, using that tool, you can build application specific integrated circuits. Okay. For everything, there is a tool nowadays, which we call generally as computer-aided design tools. Okay. The hundreds of tools are there. Always better to use tools used in industry. Cadence is worldwide tool used for analog design. Keep in mind that analog design when I'm saying. Understand it? You ask me a question, can I use Cadence for digital design? Yes, some people are using, because I don't recommend Cadence for digital design because they are new to that. Though it is some industries may use, startup may use that Cadence for digital designs, but I don't recommend Cadence for digital design. I always recommend analog design. For example, if you want to build an amplifier, if you want to build an op-amp, when you want to build a timer, 555 timers, analog circuits, what I mean in general, I suggest you to go for Cadence, because Cadence is number one tool in the analog design. If you're developing any projects using Cadence, then definitely there are plenty of job opportunities. In the very first batch when I jumped into this career, I remember that my students developed an op-amp using Cadence. They were the top one in the country. Okay, I'm saying this story maybe in 2004-5 when I first started the career. I was curious to know, work on this tool, the Cadence tool. So we learned a little bit of cadence tool, and I told my students to do project on that, and they've come out with an op-amp design. And the textbook block diagram you have seen, right? Op-amp, what are the various blocks the op-amp has got, and same blocks they have designed in the cadence tool, and they presented in the cadence design contest, and they were the top 10 in the design contest, okay, in the country, entire country. Okay. Now you know the trend has been changed. You should focus on the different advanced kind of designs. You cannot stick to once again op-amp. Okay. So cadence is the tool. When it comes to the FPGAs, there are two tools are there, which I normally recommend go for Xilinx. Okay, Xilinx is now acquired by the AMD company. Okay, AMD is is a GPU manufacturer. Okay, now they have acquired the Xilinx. Another FPGA vendor is Altera. It's Indian company, and that was acquired by Intel. Now, if you ask me which one you ask me which tool I recommend is, I suggest always to go with Xilinx because they are the leader in the FPGAs. Okay, now the Xilinx is now a company from AMD. Okay, just go to the AMD, you will see all these things what I'm saying right now. You will see plenty of FPGAs in the AMD website, and the latest FPGAs and the old FPGAs, all those things, the tools, everything you can see when you log into when you watch the AMD. Okay. Now let me come to the programming part. Programming part, you need to, once you know the Verilog program is that they must provide some simulators. First of all, to write the program, we need to have a text editor, right? Even you can use Notepad to write the program and upload that into any simulator, and you can simulate and check the results of your design, whatever the design you develop. Okay, normally it comes with simulators, and many times the test bench is also very important. What is test bench? See, when you develop an AND gate or OR gate, you can't test it. Maybe the AND gate you can do it because it has got only 2 inputs. You will have 4 possibilities. Manually, you can do the testing. What if I give you a logic circuit with say 100 inputs? How many possibilities? 2 to the power of 100. Can you do manually 2 to the power of 100 testing? First of all, writing all possible inputs 2 to the power of 100 possibilities itself is very difficult. Then how do you test every input and ensure that your design works properly or not? It's very difficult, right? Now, what industry expects is you have to develop a design. You also should develop what is called as test bench. You understand the meaning of test bench? Test bench is another Verilog code which will test the designs. Understand? Our actual design is AND gate. And for AND gate, you should write a test bench. What is test bench now? Test bench is another Verilog code which will test the AND gate. For every design, whatever you develop, like encoder, decoder, multiplexer, for all these designs, you must also develop what is called as test bench. Industry will not accept if you don't write the test bench. If you simply give the design to them, they will not accept it. Reason is, you developed a design and you also develop what is called as a test bench. Once they click on the test bench, your entire design should work. Okay, that's how the industry expects. I hope I'm clarified with why HDL. HDL is required because today's world is complexity keeps increasing. Every day, you have seen that what Moore's law said long back in 1970s, number of transistors will keep double every year. If the complexity is 1 billion transistor in the CPU, next year it will become 2 billion. Every year it is going to be an exponential growth. But the theory what Moore said, Gordon Moore is Intel chairman, he said the same thing long back in 1970s. But his law, somewhere it is becoming constant. Complexity, as he stated, every year it was not doubled actually. Now it has become like a constant. The reason for that is very many are there. One main reason is once complexity increases, testing and other becomes very difficult. Remember, today we can find a lot of engineers for doing design, but very few engineers you can find for testing. Testing and verification has become very challenging task nowadays in industry. Understand? And also job requirement, if you see, 40% job requirement is in the design field and really 60% is in the testing and verification. You understand the importance now? There's a lot more importance we have to pay for the testing and verification. People will do design. Suppose if I ask you to design multiplexer, don't you do it? Fundamentals, you will do multiplexer design. But question is, how do you test the multiplexer what you design? That's very important. Understand? Testing and verification is very important. Okay. So let's pay attention for that. And here, as I already told you, focus mainly on the Verilog. Do not look at VHDL. I just want to give a little bit history about. I don't want to speak history on VHDL since you're not learning it in this current semester. I just want to expand what is VHDL. VHDL is further. V stands for this. Look at here, somewhere here. V stands for this. It's VHDL. HDL you already know, right? Hardware description language. What is V? V stands for VHSIC, Very High Speed Integrated Circuit. Okay, that's what the expansion of VHDL. Now you can tell what is VHDL. Very High Speed Integrated Circuit Hardware Description Language. That is the VHDL. Understand? Normally, this academia uses VHDL. Nowadays, they are not proprietary language. They are all open sources, and it has got IEEE standard also. Look at this; they have mentioned already here. IEEE standard. Okay, IEEE maintains standard for the language. Even C language is IEEE standard. ANSI standard, not IEEE standard. Okay, American National Standard is the C programming. Likewise, the VHDL and the Verilog are IEEE standards. The electronic industry is the non-profit organization like IEEE is maintaining this language. Okay. Even Verilog also. Let me move to the history of Verilog because I just made a few points related to the Verilog. I don't want to focus on the VHDL. Verilog, it was started by the company called as Gateway Design Automation. And they are developed as a hardware description language. It's a very popular company long back. Okay, so that was the company developed Verilog. And later, the Gateway Design Automation was acquired by mistake. It's a Cadence. It was acquired by Cadence in 1989. Okay. Now, once it has acquired and they standardized that language in 1980, and Cadence made Verilog available to the public domain. Anybody can use that, Verilog. That's how the Cadence has made. And there are some aims. The reason why it has made the public domain is because it should become standard and it should become a non-proprietary language. There is no owners for that. Even people itself, they are the owners for that. You develop standard and you upload it to the IEEE, they will accept it. And there is a committee for that worldwide. Even Indians also, many are there in this IEEE standards. That standard they have given name as like this. IEEE standard 1364-1995. Don't ask me what is 1364. And I only know that 1995 is a standard developed in that particular year. And this was an old standard because textbook itself is old. And right now you will see the 2001 standard also. If you look at latest IEEE Verilog, you will see 2001 standard. That means whatever developments happened from 1995 to 2001, okay, every 5 years language will get updated. Okay, users will give the feedback. So based on that feedback, IEEE also will incorporate that feedback into the tool, okay, into the language. And right now, the 2001 is available right now. I don't think after that the developments have been made. Maybe they will collect feedback once and later they will standardize the language. Okay, so that's what it is happening from 1995 onwards. And Verilog is presently maintained by Open Verilog International (OVI), what we call. And Verilog is, as I told you, its roots lies in the C programming language. Analog extensions to Verilog is underway. I don't think it will be possible. What do you mean analog extension? Any analog circuits can also be modeled. Right now, you can only do digital design, like as I told you, starting from simple gate to the complete laptop can be built on the Verilog. Okay, so that language will support it. But analog, you can't do it. If I ask you to model a capacitor, you can't do that using Verilog or VHDL. Understand it? For that, it's that's underway. But I think in future they will do even that. Okay, there are even textbooks for Verilog analog modeling also. Nowadays the textbooks have come. You can also go through those textbooks and try to do analog modeling. Okay, there are some tools also for that. Okay, let me now move on to the structure of the HDL module. So far you understood the basic, the history of the Verilog module. And let me look at the structure, how to write the program, what are the key things to note to write the program. And see, whatever I say theory here, if you don't put it into the practice, it will not become useful. I may say, a lot of motivating things to you about Verilog and VHDL and in general for digital design, unless if you don't have a tool relevant to this Verilog simulators, and if you don't practice it, it will not become useful. It will just, you will listen from 1 year, and after 3 months or 4 months, you will forget even Verilog itself. Okay, so don't do that. And I suggest you, if you have a laptop with you, Just like I've installed a couple of tools, I will show you, demonstrate it few tools, simulators, and show you on the simulator itself how to write Verilog program and simulate it. And I will show results also for few designs. But you can extend that to do complex designs as well. Okay. HDL, as I told you, its language is related to the, more or less, it's similar to the C programming language. It's high level language, first of all. If you are familiar with, like, C programming with all syntax, semantics, starting from if, low, if statement, for statement, while statement, okay, functions, how to write functions, how to write procedures, understand here. If you understand those things in C programming, all of you are good at C programming? Yes or no? If not, please, now C has become like a default. Understand? As a being engineering student, you must learn default C programming language. That's the, the basis for all other languages, like even Verilog also. Understand? Don't learn reverse, learning Verilog and then going to the C. Start learning C program and then you can move on to the Verilog. Now don't spend time in, right now. I assume that a few syntax you can understand without even C programming, but pay attention and become familiar with C programming as well. And text editors we can use, there's a lot of text editors. Notepad itself we can use and write a program. Which one? Yeah, Virtual Studio, so many are there, simulators. Okay. You can use various simulators. Even if without tool also, if you just have internet connection, you can just compile and run the C programming. Lots of flexibility. Have you heard about Google Colab? So you can even learn Python program using that, right? And Google Colab will provide even GPUs also at free of cost. Understand here? So why don't you use that opportunity? Understand? And even there is a Copilot. Have you heard about it? GitHub has come out with Copilot. You can also use that. It's free for students. All these things you must explore. And also, be attached with some IIT and other premier institutions, especially the faculty and the student groups. You will get to know what are latest developments in the field. Don't be blind and attach only to the VTU colleges. I also suggest you to get linked with IIT and IAC faculty members and student groups, so that you will get to know what is happening in that field, especially electronic field. Okay. Okay. This is the fundamentals. Once you have a text editor, once you have simulator, you can write the Verilog program and you can compile that. Let me show the structure of the, I don't want to go for VHDL, straight away I will move to the Verilog. Yeah, here you can see the Verilog structure. Is it complex? See how simple it is now? This code, this explains you an off adder. Look at here, this code explains you the off adder. How to start with? Start with a module. Just like in C program, you start with a main function, right? Similar to that, you should start with the module, and this is a module name. It is user defined. User can give any name as module name, but don't try to give the keywords, because in Verilog simulator, certain things are identified as keywords. Keywords are standard words which a tool has inbuilt. Don't use that inbuilt built-in functions as user-defined names. Example, if you use here A and D, it is a predefined function, AND function. If you use that, tool will complain. Tool will say that you are using my function, and you should avoid using those things. And you can give anything here, but don't start with numbers here. Always better to start with some alphabets. Even though the alphanumeric is allowed here, I always suggest to use whatever design you have. My guide suggested me all these things, even though he's expert in this Verilog. Okay, he suggests me all these tiny things also to me. Okay, he always suggests don't write this. Start with numbers, and this design should tell you what kind of design you are developing. The name should tell you. Okay, even after the 10 years or 15 years, you should be able to recall that what name you have given, and you are building your own library by developing these kind of things. Once you develop this C half-adder program, store it in your library and develop test bench for this. You did not simulate every time the design. You just simulate the test bench. It will give complete results of the half-adder, because test bench and this design will be attached with each other. Okay, to connect with each other, then only This is the design will run. Okay, so this is a bracket. You can see that within the bracket you have defined input output of an half adder. So when you are writing Verilog code, you should imagine like a block diagram of a design. Understand here? Block diagram contains some input and some output, right? Here inputs are interpreted as I1 and I2. You can give your own names as inputs, but here we have given as I stands for input, therefore I1 is first input, I2 as second input. Half adder requires what? Two inputs, two outputs, right? These are the inputs I1 and I2. This will accept binary data I1. I1 can take 0 or 1. I2 also can take 0 or 1. And similarly, it will produce results as O1 and O2. O stands for output. Okay. So we have for half adder two inputs and two outputs. I can show you that using a block diagram something like this. This is a block diagram of an half adder. And we have got I1 as input, I2 as another input, O1 as output, O2 as another output. Understand? You already know working of this, right? How I1, I2 are connected with the O1 and O2 with the help of truth table or with the help of Boolean equation. You know various methods how this I1 and I2 are related to the O1 and O2. That's what you are describing in the logic. Understanding? So let me go through that. All have understood now first part, structure of the Verilog program outright. This structure is similar. Any design you will take with a simple gate to the complex design, the structure remains same. You should start with a module. This is a standard word. Module name, you can give any name, but it should reflect your design. And within the bracket, you are defining what is input and output for your system. Always see when doing digital design, complex digital design, there are two approaches what we have. What are those two approaches? Top down and bottom up. What about these two things? Top down approach and bottom up approach. What do we mean by top down approach? Top down approach is similar to the thing, if I give a complex job to you, understand? Suppose, I will tell you that clean this room and arrange this desk properly. Maybe it is a complex, you will distribute this work among yourself, right? Same way, when I give complex design to you, you divide that complex task into the simple tasks, subtask what we call. Understand here? You start doing one subtask and finally you achieve the complex task. That is called top-down design. Breaking the bigger things to the simpler one. Understand here? A complex design, you are breaking into a simple task here and implementing each subtask so that you achieve the complex task. That is what a top-down approach. You are starting from the top and reaching the bottom level. Bottom level means it's a gate level, till gate level. If I ask you to design an 8-bit ALU, that's your top level system. Understand here? And also when I say 8-bit ALU, you must also ask me complete specifications of this. One important thing, the normally industry people ask you is, you have to write down the specifications. Simply if I say design 8-bit ALU, don't blindly go and design 8-bit ALU. You must ask me that how many operations my ALU should do it. Understand here? When I say 8-bit ALU, if I say 10 operations, example is when I say addition, 8-bit addition. When I say multiplication, 8-bit multiplications. I should say number of operations also. And I will also give you that whether my ALU should have an enable signal or not, start signal or not. These are all imaginary inputs you are supposed to give. Understand here? See, to build a laptop here, don't you think that there is a push button, a power button here? Understand here? Whatever user needs, that has to be incorporated to your design also. When I say ALU, there must be some enable, right? Why enable is required? How do you switch on and switch off your, the ALU? There must be some enable. There must be some reset button, right? These things nobody will tell you that. You must imagine that, and you must also imagine what all other signals needed, and you should develop a block diagram first. On paper, you must develop block diagram first. Okay. My mentor told me all these kind of things. He will never allow me to go to the computer and start doing programming. Whatever the idea I have, I must put it in the paper with the block diagram only. And then he will tell me to develop the micro level diagrams. One is top level block diagram. My entire idea is conceptualized in the top level block diagram. And when you go to the micro sub levels, every level should be defined first on the paper itself. Then you will get a complete picture when you reach the micro levels with all wire connections, with all block diagrams, imaginary kind of blocks you should write. Understand here? And you will understand complete picture of your design. Once the complete idea is there on the paper, then you can go and identify the proper tool, and you can start coding them, one by one. Suppose if there's a group of students are there, one student can take one particular design, another student can take another design. That's what industry also will do, right? A single project will not be executed by one particular industry. They will distribute for different teams. Maybe one team sitting in US, another team may be sitting in India. Understand it? At a time the task will be executed. Same way, a top-down approach is a bigger task can be divided into simpler tasks. A bottom-up is just a reverse of it. Your small task, as I told you that when you develop an adder, make this as one library, one component of your library. And when you develop when you say full adder, that's another component of your library. Like that, maybe after 1 month you might have developed your complete the components of your library, right? Now I will give you some task to you. For example, I may ask you to build say multiplexer. You already have a library of components with you. What to do is assemble them, group them, and build your design now. It will take less time. That's called bottom-up approach. Okay. So either styles you can follow, top-down or bottom-up. Nowadays in industry they will follow both the approaches. They will not stick to one particular approach. So top-down also it is required, and bottom-up also it is required. Why? Because time is very less. Within a week, within the 3 days, they have to complete the project. Unless if you don't follow these both approaches, there will be hundreds of people working on one particular project because time is very important for them. Okay. As I told you, you have to incorporate that style even in your lifestyle also. Industry environment, industry atmosphere should come in your lifestyle. Then only you will become a complete professional. Otherwise, you will not be a professional guy. Okay. Fine. I hope you understood these things. Now remember here, though I have defined here both input and output here, order is not important here. You may ask a question here, should I write first I1 or should I write I2? No. It all depends on you. Order is not important. Tool will not compare anything about the order here. Understand here? Always having minimum number of inputs and outputs is always better. While doing digital design, don't go for more number of inputs. Don't go for more number of outputs. Understand here? More input pins, your IC becomes complex. Always have less number of pins, less number of wires, less number of components. That's what our aim in the electronic design. And all components must work at high speed. You can't design, a one component. If it is working very slow, that will kill your entire time, entire performance of a system. Understand here? You must ensure that all your designs, library of components, what you are developing like this, will work at a very high speed. In such a way, you must write a program. I'll also tell you two concepts what I've used in my research is a pipelining and parallel processing. What about these two things? Pipelining, parallel processing. That's what normally in industry, these two things are missing. Understand? A software guy will write a program without focusing, without paying attention to the pipelining and parallel processing. Though these two things, for a beginner, it becomes very difficult, but later on, if you incorporate these two things into every design, you'll become expert in the programming. You take up any old design, understand here? Identify that where all you can apply the pipelining concepts, where all you can apply the parallel processing kind of concepts. Definitely you can improve the performance by twofold, threefold. That's what I did in my research. I improved my performance, though the people say that you have developed the same idea what others have done. But you see the performance of my system, because of incorporating the pipelining and parallel processing system, my performance is nearly the fourfold better than the existing one, right? So you must learn now what is pipelining concept. It takes a lot of time. Please pay attention to all these new things. If you are expert in these things, definitely I will tell you that your industry will not do these kind of things. Okay. Pay attention for these two things. Pipelining is very, very important, let me tell you. Even if you simply design an adder, it doesn't work. It may work normal, it may do a simple addition, but it may not be the high-speed adder. How to develop high-speed adder? incorporate pipelining concept into the adder, develop pipeline adder, develop parallel processing adder. Understand? If you do that, definitely the design becomes high performance. This is very simple design. I told you adder is not important, but Verilog is case sensitive. So that's look at here, double slash like this indicates comment line. If you want to comment, you can do this. And there is one multiple line comment also. I will show you later on. This is single line comment. This entire line becomes comment. And this is a line terminator, semicolon. You can write entire program in single line, but that's not good practice, right? You will terminate the line. This shows that this line has been terminated and new line has been started here. Always in any programming language, this is common, right? There must be a line terminator. That's nothing but semicolon, line terminator, like your house. Understand it? You should stop and proceed next. This is one line terminator. Then we have input, I have expanded which is input and which is output here. Input is I1, input is I2. You can also define this I1, I2 here in a single line. But here, to make it, explanation easier, we are defining the two different lines. Output O1, output O2, these are all have with semicolon. That's a line terminator. See, actual logic of the program is only these two things. How this program has been written? Just based on half-adder Boolean equation, nothing else. What is the Boolean equation for half-adder? Sum is nothing but XOR, right? Look at here, the add symbol here. I see tiny add here. That's an XOR operation. Look at your AND operation. Ampersand. These are called bitwise operators. What is bitwise operators? Each bit it will do. I told you this I1 is, see, it can be 0 or it can be 1. I1 also can be multi-bit also. It can be 3-bit, it can be 4-bit. If this is 3-bit, I2 also should be 3-bit. There cannot be random sizes, non-uniform kind of sizes. Ensure that I1 and I2 are of same size. If you don't do it, define anything here, its default it is a 1-bit. It can be 0 or it can be 1. So I am doing here I1, I am XORing with I2, and then I am assigning to the left side, which is O1. This is what it implements sum of half-adder. For the carrying of an half-adder, it is AND operation. I am ANDing I1 with I2 and assigning to the O2. Look at it, there is an assign statement here, which is a keyword in Verilog. The tool understands the moment you assign, use a word assign here, it looks for two things. Left hand side, destination, right hand side is computation. It computes this and assigns to the left hand side. Understand this? Very simple two-line statement for half-adder. Look at now how the things are very simple now. What tool will do after compiling this? Compiler will check only the errors, right? It will not check any other thing other than error checking. Compiler is basically a language translator. Understand it? It checks when you compile this code, it checks whether you followed Verilog standard or not. If you make any mistakes, as I told you, in place of this writing keyword or writing comma here, tool will understand, check for those things. If language is not written properly, it will complain and it will rectify that. Okay. Once it is done, this is the end of the program. Start with the module and end with the module, end module. It's a very simple program for half-adder. Likewise, you can even model, complex designs. Any questions about this? No questions? Already told you Verilog is case sensitive. Uppercase and lowercase are different in this case. It is case sensitive. Okay. And what else? Order is not important. That's what it is told here. You can see here. Here we have not followed any order here. Okay. There is no order we have followed here. And semicolon, as I already told you, it is a line separator, a line terminator. And also here you can see that we have not even followed order here also. Are you seeing here? Earlier we declared input first, then the output next, right? But look at here now, output we have declared first and the input next. Order is not important here. Okay. And what else? And you can see here what changes we did here. Instead of having different outputs like this, you can also do it in a single line like this. Okay. And input also you can declare in single line like this. Okay. Any questions about this? You can also have input output. There are situations wherein which you want to have both in out also, especially in latches, flip flops. You want to make certain ports as output and as well as input because you are connecting feedback, right? In such case, you have to make in out. Yes. Okay. You will see that when I show you the modeling of latches and flip flops, I will be using signal names with in out. We have a Q and Q bar. You remember in latch, those Q and Q bar should be defined as in out because they're also output. They're also input for the other, the input of a gate. Okay, that's why you must declare them as in out. Now let me move on to the operators. Any questions about the basics and fundamentals of Verilog? Before I move to the operator, I just want to show you the tool, which is a commercial tool which is used in industry. This is what the tool. Look at here. Model sim. What I will do is I will show you. This is the model sim. You can see here. I'm using here 10.6D version. This is not freeware. It is a proprietary tool by Mentor Graphics. You can see there's a Mentor written here. Okay. And initially, when you install the tool, you will not find this work library. For that, you can create that work library. And I have created that work library. All your compiled code will be appearing in work library here. I'll just open one of the design. Look at here. This is very simple. How this code works. Can you see this one? Yeah. Module. I've given some name here main. Y is the output, A and B are the inputs. Output is again Y, 3 is to 0. I have just 4 bits altogether. Okay. It's very simple design, not so complicated. All of you understood why this is 3 is to 0. I'm expecting I'm giving input something like this. 4-bit data I'm giving. Like this. 4-bit data. I'm giving that for Y output is like this. And what else we have? A and B also it is 4-bit. A also I'm giving this sort of data like this. 4-bit. And B also I'm giving as like this 4-bit. This is 3, 2, 1, 0. That's why 3 is to 0 I'm mentioning that. Are you getting it? 3 is MSB and 0 is LSB. Look at here. 3 is to 0. Whatever the 4-bit number you give like this, okay, the 3-bit position will become MSB and 0-bit position becomes LSB. Understand? What if I declare something like this? 0 is to 3. I will start with LSB, end with MSB. Suppose if I write number like this is LSB, this is MSB. If I declare like this. Okay? Here I have declared as 3 is to 0. 3 is to 0 means it is just opposite. So I have given here, this is our MSB, this is LSB. Understood this? 4-bit data I am giving for Y. My output will be 4-bit. 4 wires coming out. A and B are also 4-bit. 4 wires for A and 4 wires for B. Totally 8 are there. What I am doing here, operation is simple and operation. Let me show these results. Start simulation. I want to compile this before I do the simulation. Compilation is very easy. You can just see that compile. It asks me the live where my code is there. My code is main. See, it is compiled already. No errors. I'll make some intentionally some errors. You can see here. I'll remove just semicolon here. Save. Seeing now error it has shown. It's showing some semicolon is missing over there. I'll add up semicolon and again save, compile. Now it is fine. Compilation means it checks only language, whether it's correct or not. Now I want to verify this, whether this code is working according to my design or not. Please don't just talk there. Boss, please listen. You are your own world, dream world. Huh? But come to the BMS IT. All right, let me show the simulation, start simulation. And here compiled code, as I told you, it will appear in the work. Go to the work, see already it is there, main. I'll just say OK to that. It will open a couple of windows here. Are you seeing here various windows have been opened? One is, this is object window, process window, and there is one more which has opened here. This is called waveform window. Understand? So here what you can do is, now you can see all our input lines are appearing here. This is output line. Are you seeing here 0, 1, 2, 3 bits? I showed you that 3 down to 0, right? You are seeing that. And also look at A. It is now 4-bit. This A of 0, A of 1, A of 2, A of 3. Similarly, I also have B. B of 0, B of 1, B of 2, B of 3. Each one of these lines will take binary data. Okay. Now what I will do is, now I'll just go to the add to. I will copy the same thing to the waveform window. Now you have seen waveform window, same signals have come here. Are you seeing that? Now where should I give input now? I should give input to A and B. What I will do here is, now I'll go to the, I'll prefer the radix as binary, and I will force, look at here now. I have given some data, 4-bit data like this for A, and I will give another 4-bit data for B. I will force, I'll give as 0, 1, 0, 1. I will show the output now. Here there's a run. Are seeing now? What did I give there? Just look at your results. Yeah. Just you can see the results. Okay. Now it is doing bit by bit AND operation here. Okay, next class I will show you detailed, how exactly output is appearing here. This is 4-bit input. A and B is 4-bit. And the result also you are getting as 4-bit. Look at here. Corresponding bits you can verify here. I'll just move this window a little down. Now you can see here, A of 0 you can see 1, B of 0 you can see which is 1, and you can see here Y of 0 it is 1. Are you seeing that? Just see the 0. This is 1. 1, this is 1, this is 1, this is also 1. I am doing AND operation here. Like that you can verify each one of these inputs here. At a time I am implementing just 4 input AND gate. Okay. Any questions about this? I suggest you to install this kind of tools and verify your results. Have some hands-on experience using these tools. I'll stop simulation. Like that I have developed a couple of designs. I'll show you a few designs in the next class. That's all for today's class. I will continue in the next class.